Hello everybody. Today I shall discuss the condition under which a straight line becomes tangent to a particular conic. Okay, I am going to discuss the condition under which a straight line, a given particular straight line, becomes a tangent to a given conic. Suppose we are given a conic s is equal to 0 and a straight line like this lx plus my plus n is equal to 0. Hmm. And it is given that this straight line becomes tangent to the conic s is equal to 0 at the point x1, y1. Okay. Now, what conditions should be satisfied so that this equation, say equation number 1, this equation number 1, that is the straight line Lx plus My plus n is equal to 0, becomes a tangent to the conic S is equal to 0. We know that equation of tangent at the point x1, y1 on the conic can be written by this formula t is equal to 0. Elaborately speaking, this would be the expression of the formula t is equal to 0. If you try to separate the coefficient of x, this would be the expression ax1 plus hy1 plus g. And then the coefficient of y would be hx1 plus by1 plus f into y, and the remaining constant term would be gx1 plus fy1 plus c. This would be the total elaborate expression of the tangent t is equal to 0 at the point x1, y1. And it is given that this equation number 1 is a tangent to the conic s is equal to 0. Therefore, we actually got two equations. One is this equation number 1, another is this equation representing a single tangent at the point x1, y1. Therefore, these two equations must be identical to each other. I mean, the coefficient of x, the coefficient of y, and the constant term must be proportional. If you compare these results over here, you see over here, you see this is the coefficient of x, that is actually our L, and this is the coefficient of x, that is ax1 plus hy1 plus g, and that is the coefficient of x. So these two coefficients, the coefficient of x obtained from second equation divided by coefficient of x obtained from first equation. This ratio of these two coefficients must be is equal to the ratio of the coefficient of y, that means this kind of expression hx plus by plus f, this quantity divided by m. So this is the value. Again, the constant term, this quantity divided by this n, this constant term divided by this n, all these three should have same value. Let us call them this common value as equal to lambda. Okay, then you see, if this lambda is equated with this first ratio, then we will get this kind of equation: ax1 plus hy1 plus g minus L into lambda, this denominator L multiplied by this lambda. Okay, L into lambda would be is equal to 0. This gives the first equation. Okay, similarly, if this lambda is compared with this second ratio, in that case we will have this second equation hx1 plus by1 plus f minus m into lambda is equal to 0. Again, if it is compared with this third ratio, in that case we will have the third equation gx1 plus fy1 plus c minus n into lambda is equal to 0. Got it? And we already know that this point, this tangent and Lx plus my plus n, this straight line is a tangent at the point x1 y1. Therefore, this point x1 y1, this point x1 y1 must lie on this straight line Lx plus my plus n is equal to 0. What I'm trying to say is that x1 y1 must satisfy the equation Lx plus my plus n is equal to 0. Okay, x1 y1 must satisfy this equation number 1. Got it? And therefore we have this result Lx1 plus my1 plus n is equal to 0. So we actually have four results, four equations. These are the three equations and this is the fourth equation. We have four equations involving three unknown quantities. The first unknown is x1, second unknown is y1, and the third unknown is lambda. These are three unknown quantities. Theoretically, we can say that we can eliminate or we can solve the values of and solve and find the values of x1, y1, and lambda from these three given equations. And then afterwards, we can put the values of x1 and y1 in this fourth equation. Then all the unknown quantities x1, y1, and lambda, all these three unknown quantities will be eliminated from these four equations. Okay, and after eliminating the three unknown quantities x1, y1, and lambda, what we get, we will get a determinant, this kind of determinant. The determinants are actually the coefficients of x1, y1, lambda, and this constant over here. The third, this third column corresponds to this constant term, this g, then this f, then this c. Got it? The first column corresponds to the coefficients a, h, g, these three coefficients a, h, g, and the coefficient of x1, that is actually l. Got it? So we get this first column A, H, G, and L. Similarly, we get the coefficient of y1 as the elements of second column. These are the coefficients of y1. This is H, then B, then this F, and over here this M. And similarly the coefficients of last this lambda L, M, and N. The coefficient of lambda are minus L, minus L, and minus M. Actually we should have certain minus sign over here, but due to the fact that there is no lambda in this last equation, so we can say that plus or minus 0, we can take all this minus common and ultimately we can make them plus. Got it? So we can simply say that we actually got this determinant. And if we expand this determinant, you would get this kind of expansion. You don't need to remember this expansion. You try to remember this this determinant only. Got it? Over here, the coefficients A, this B, this C, these are actually the cofactors of small a, small b, small c, etc. in this determinant, and this is the well-known determinant delta. This is a well-known determinant delta. So that is the condition. Just you need to remember this much. You need to remember this much. Got it? You need to remember this much. Okay, you need to remember this determinant. This is the condition under which a given straight line Lx plus my plus n is equal to 0 becomes tangent to the conic S is equal to 0. Is it clear to you? The condition of tangency?
Yes, sir.
Okay. Next, we need to discuss something in elaborate fashion regarding the normal and some results related to tangent, conormal, and subtangent, subnormal, etc. So that actually involves the discussion not directly related to this chapter, but indirectly they are related to this chapter because they are related to tangent and normal. And you will find the detail of this discussion in the chapter tangent normal. Although officially it is not involved, it is not included in your syllabus, but I am just going through few definitions in tangent and normal, few results and definitions related to tangent and normal. I am not going in elaborate fashion the detail of tangent and normal. Okay, officially it is not included, but as because the general equation of second degree is related, is included in your syllabus, so some results related to tangent and normal should be discussed over here, because this chapter is not individually included in your syllabus. Hmm. So I'm going through few results from this chapter. Only few results from this chapter. Hmm. Over here, we know that equation of parabola y squared is equal to 4x. Hmm. We know the equation of parabola y squared is equal to 4x, and we know that the tangent of this kind of equation can be written by the formula t is equal to 0 at any point on line on that curve. So if we apply that formula over here, then you will get the equation of tangent. And most of the time, the equation of the point under consideration is taken as this kind of parametric points. That means x is equal to 80 square, y is equal to twice 80. Got it? So x is equal to 80 square, y is equal to twice 80. Or in other words, we can say that x1 is equal to the point 80 square and y1 is equal to the point twice 80. This is the equation of tangent to the curve, to the parabola at the point x1, y1. Okay, this is the equation of tangent to the parabola at the point x1, y1. Now, if particularly the point under consideration, that is the point p x1, y1 is taken in parametric fashion, that means x1 is equal to this expression 80 square, y1 is equal to twice 80. In that case, we can put this x1 is equal to 80 square, y1 is equal to twice 80 in this equation of tangent, and ultimately we will get this kind of equation. If possible, you can remember this formula. You can directly apply this result in your exam. Okay, if possible. I am not giving any compulsion to you. I'm not stressing this one, but I'm not imposing this one. But if possible, if you want to remember this formula, you can remember this one, and then you can directly use this result in your exam, if possible. If it is not possible, because for me I found that it is not possible to remember the formula. Generally, I used to remember this formula. Okay, and then I put x1 is equal to 80 square, y1 is equal to twice 80. It depends upon our capacity. Hmm? I have very limited capacity, so I generally try to remember the formula t is equal to 0. I always remember this formula t is equal to 0, and then we put this kind of parametric expression 80 square twice 80. Then we get this kind of equation of tangent to the parabola at the point 80 square twice 80. Okay, and regarding normal, let me show you the equation of normals over here. Where is that equation? Just a minute. Many results are there. You can, if you have any extra time, you can go through these results. They would just enrich your capacity. That's all. This is over there. Equation of normal. We know how to find the equation of normal. And if you have the equation of tangent, from that equation of tangent you can find the gradient of the tangent, and if you know the gradient of the tangent, then from that equation you can find the equation of normal to the curve. And again, in this would be the equation of normal. Okay, I'm not showing the inter deduction over here. You all know how to compute the normal. I discussed them in last classes. So over here, if we have this kind of point 80 squared twice 80, in that case, after putting y1 is equal to twice 80 and x1 is equal to 80 squared, you can deduce the equation of tangent in this fashion. This is also a formula. If possible, you can use this formula in exam. You can directly use this formula over here in exam. And you see, you observe over here, you see this minus t. This is an important observation. This minus t, that is actually the coefficient of x. This minus t is the gradient of the normal. Okay, so minus t becomes the gradient of the normal. The coefficient of x is the gradient of the normal. So suppose if it is given that m is equal to the gradient of the normal, then just by putting m is equal to minus t, you will find that this equation of normal can be converted into this formula. M is equal to, just by putting m is equal to minus t. M is equal to minus t. Just by putting m is equal to minus t or t is equal to minus m, you will be able to convert this equation into this kind of equation. Okay, so these are the two highlighted equations that you can directly use and apply them in your examination. Got it? That's I wanted to say over here. And there is one more concept that is called the conormal points of a parabola. Conormal points of a parabola. I'm trying to firstly discuss something related to normal. Then I shall discuss something related to tangent. Okay, some results that you need to remember related to tangent and related to normal. So over here, as I'm presenting this portion of normal, so let me first complete the discussion related to normal. All right. So over here, there is a concept that is called the conormal points. What is the conormal points? Conormal points of a parabola, maybe hyperbola, maybe ellipse. What are conormal points? You see, suppose you have a parabola like this. Suppose you have a parabola like this, and from any point, suppose from any point, we can mathematically prove this result. That would be a matter of two lines only. Now, suppose it is the point P. I don't know what coordinate has been taken. Yes, suppose this is a point P, and maybe this is the coordinate of the point x1, y1, right? Let x1 and y1 be the coordinate of this kind of point P. Got it? Let x1 and y1 be the coordinate of this kind of point P. This is the coordinate of the point P, x1, y1. And the question is that how many normals can be drawn from this point P on the parabola? I am repeating the question. The question is that how many normals can be drawn from the point P on the parabola? If you look at this picture, maybe though the picture is not very good over here, maybe this is one normal, maybe this is another normal, and maybe this is the third normal. We can prove that three normals can be drawn from a point x1 y1 on a parabola. We are going to prove this result. In fact, this is a very important result that can be selected as an objective question in your examination. Maybe 3 marks or 2 marks or at most 4 marks. It should have maximum 3 marks, I think. Okay, three normals can be drawn on this kind of parabola. Now, how to prove this result? Suppose, oh, I deleted this picture. Suppose this is the parabola and this is the point P, having the coordinates x1 and y1. And we know that equation of any point, suppose this is a tangent, this is a normal at any point, what would be the equation of what would be the coordinate of the point? Suppose at square, hmm, at square, then twice at, twice a t. Suppose this is the coordinate of the of this point, and we know that equation of normal that can be written, equation of the normal at this point. Suppose this is the point, say capital A. Equation of the normal at the point capital A can be written in this way. Hmm. Any point capital A can be written in this way. Now, if it passes actually in this fashion, any point, this is suppose capital A, that can be written in this fashion. Hmm. In this as this equation number one. Now, if this point x1, y1, this is the point P having coordinates x1, y1. This is the point P having coordinates x1, y1. Now, if this point x1, y1 also lies on this normal, okay, on this normal, suppose this is the normal. If this point P lies on this normal, then the coordinates x1, y1 of the point P must satisfy this equation number one. Got it? So we can put x is equal to x1 and y is equal to y1. Ultimately, we will get this kind of result. X is equal to x1, y is equal to y1. Got it? So ultimately, we would get this kind of result. And again, I deleted the picture. I'm very sorry. Hmm. And over here we can draw from this point P. This is the point P, x1, y1. Again, you see, if we try to write them as an equation involving t, then this would be a cubic equation. T cube is there. This is the equation that has been written. Everything has been kept on the left hand side. So you will ultimately get this equation number 2. This equation and this equation are actually same equations represented in different fashion. That's all. So over here, how many values of t is possible? How many real values of t is possible? Over here, this is a cubic equation. So we would ultimately get maximum 3 values of the variable t. Suppose t is equal to t1, t is equal to t2, and t is equal to t3. So for t is equal to t1, you may get 1 point on the curve. For t is equal to t2, you may get the second point on the curve. And for t is equal to t3, you may get the third point on the curve. Got it? What I am trying to say is that from T1, T2 and T3, you can draw 3 normals passing through this point x1, y1. So at most, maximum 3 normals can be drawn from the point P on this parabola. Got it? And these 3 points, this is one point, this is the second point, and this is the third point. The point represented by the parameters t1, t2, t3, these 3 points are called the co-normal points of the parabola. That means the co-normal points are the points on the curve. In this case, I am considering a parabola only. This same definition is valid for any other curve as well. Okay, so co-normal points are actually the points on the curve, so that if we draw normals or at that points, then all these normals must pass through a single point. Got it? All these normals must pass through a single point like P. This kind of points are called co-normal points. And over here, I have proved that maximum 3 normals can be drawn in case of a parabola.
স্যার এটা হাইপারবোলা এলিপস এদের ক্ষেত্রেও প্রযোজ্য?
Yes, of course, this is applicable to hyperbola and as well as for ellipse. Let me show you that portion over here. Let me delete this part. Uh, this is the definition of co-normal point that I discussed over here. Um, Suppose in case of, this is the result in case of ellipse, x square by y a square plus y square b square is equal to 1. And we know that a parametric point, just like 80 square twice 80 in case of parabola, there is one parametric representation of ellipse as well over here. There is a parametric representation. That parametric representation is a cos of theta, b sine of theta. Hmm. So any point can be considered as a cos of theta and b sine of theta, and we know how to compute the equation of normal. This would be the equation of normal at the point x1 y1. So we can put x is equal to a, x1 is equal to a cos theta and y1 is equal to b sine theta. Then you will get the equation of the normal at the point a cos theta b sine theta. Generally, this point is simply denoted by theta. We call it theta point. Theta point means the coordinates should be represented by the parametric fashion. That means a cos theta b sine theta. Got it? So in case of ellipse, this would be the equation of the normal at the point theta. We call it theta point. And now over here, just similar to the previous discussion, this would be the equation of normal. If you this equation, if you consider this equation, okay, then this equation can be further manipulated, and ultimately in place of 1 by cos we will have sec, in place of 1 by sine we will have cosec of theta. So this would be the equation of normal to this ellipse at the point theta, at the theta point, at the point theta. Okay. Now again, say let me draw one picture for you. Maybe this is the picture of ellipse, and this is any point, suppose, and suppose at a point theta, this is the theta point. This is suppose theta point. We are drawing a normal, and suppose this normal p, this normal passes through the point p having coordinates x1 comma y1. Okay. Now we are choosing in a little we are choosing this parameter in a little different fashion. Suppose we choose t is equal to tan of theta by 2. We know sine theta can be written as 2 tan theta divided by 1 plus t square. This kind of expression will be valid. Sine theta is equal to, sorry, not 2 tan theta, rather 2 tan theta by 2. We know sine theta can be written as 2 tan of theta by 2 divided by 1 plus tan square theta by 2. Fractional uh, fractional angle. So if t is equal to tan of theta by 2, then sine theta can be written as 2 tan theta by 2 divided by 1 plus t square. Similarly, 1 plus t square means 1 plus tan square theta by 2. Over here, cos of theta can be written as 1 minus tan square theta by 2 divided by 1 plus tan square theta by 2. So 1 minus t square divided by 1 plus t square. This would be the representation of sine theta and cos theta if tan theta is taken as equal to t. Okay. And if we know the expression of sine theta and cos theta, we can compute the expression of sec theta and cosec theta over here. So we are putting this expression and making this one in a simple version. Then we will have this kind of result. So ultimately, we will have this kind of result. And from this result, what you observe over here, you just try to observe it little carefully. T squared is there multiplied by t. So this is the right hand side is cubic expression involving the variable t. The over here on the left hand side, maximum t square and then t, that is again a cubic expression. But over here, t to the t square and t square. That means if you multiply them, ultimately you will get t to the power of 4. So this equation, this highlighted equation within this box, red box, this equation would be a fourth degree equation involving t. Okay. So if we want to solve this result, we would at most get 4 different real roots of the variable t. and corresponding to each value of t from this formula, okay, corresponding to each value of t from this formula, we will get we may get four different values of theta, say theta 1, theta 2, theta 3 and theta 4, and each and every different value, sorry, I again deleted this picture. And for each and every different value of theta, we will get 4 points. Maybe the first point is equal to theta 1. This may be the second point. This may be the third point, and this may be the fourth point. So that if we draw normal from these 4 points, then all these normals would ultimately pass through a single point, say capital P, and this kind of points are called conormal points. Therefore, as because we get four different values of t, therefore we would get maximum four conormal points in case of an ellipse. Got it? And similarly, in case of hyperbola as well, if you consider the same technique, I'm not going to discuss the entire technique. In case of hyperbola as well, if you consider the four, where is the deduction? Conormal point for ellipse, ellipse. Then yeah, this is the deduction for hyperbola. I'm not going to the entire deduction. Over here again, t is equal to tan of theta by 2 theta. It has been taken in this way. Then cos theta and tan theta can be written over here. If you know the cos theta, you can compute sec of theta, and the tan theta expression is already there. So again, you will get fourth degree equation involving the variable t, and for this kind of fourth degree equation, you would get maximum four different values of t, and for all these four different values of t would ultimately give us four different points on a hyperbola, so that if the normals can be drawn on that points, then all these four normals would pass through a single point x1 y1. Got it? So in case of hyperbola as well, we will have four different conormal points. Is it clear to you?
Yes, sir.
So next, that is the definition of subtangent and subnormal. Okay. Actually, this definition of subtangent and subnormal can be defined for any curve. You will ultimately get this kind of definition in the application of calculus. There is a chapter tangent and normal, and you will get all these results in that chapter. Hmm. But in this case, generally one objective question is selected, and I am going to discuss that result over here. Hmm. What is subtangent and subnormal? If you consider this picture, suppose this is the curve parabola. This is the curve. Say this curve, this portion. This is the curve parabola. Okay, and from any point P on this parabola, we may draw a tangent and we may draw a normal. Although the picture is does not look like a normal, but PG is the normal over here, and PT is the tangent. Okay. Now this is the axis or x-axis. Generally, if you consider the equation y square is equal to 4ax, ax in this fashion. In that case, this becomes the axis of the parabola as well as the x-axis. This would be the x-axis or the axis of the parabola. Okay. Now, if we consider the coordinate of the point P, suppose over here the coordinates of the point has been taken as at square x coordinate and twice at is equal to y coordinate. Then y coordinate means this much height would be is equal to the y coordinate. Okay, as because this axis is the x-axis, and maybe one this kind of line may be the y-axis. So this twice at, this much would be is equal to the height of P from x-axis, or the distance of the point P from x-axis. So Pn would be is equal to twice at. Okay, and if x-axis cuts the tangent at the point T and the normal at the point G, in that case this much length, this much length is called the length of the tangent. This much length is called the length of the normal. Okay, PT, this length is called the length of the tangent. PG, this is called the length of the normal. Okay, along with that, distance from T to this point N, this Tn, this is called subtangent, related to tangent. Subtangent is always adjacent to tangent. Okay, and this much length in between N and G, this much length is called the subnormal. TG, this much length is called the subnormal. Subnormal is always adjacent to this normal. Okay, so this much length TG is called the subnormal. This is our subnormal. This is our subtangent. This is our tangent, and this is our normal. So we have four definitions. Actually, these distances are actually called the length of tangent, length of normal, length of subtangent, and length of subnormal. Now, how to find the length of subtangent and subnormal? In that case, we need to find the coordinate of T, the coordinates of G, and the coordinates of the point N. You see, the coordinates of the point N is easy to find. Why? Because we know the coordinate of the point P. The x coordinate of the point P and the x coordinate of the point N must be same, because these 2 points lie on a straight line parallel to y-axis. Okay, therefore, as because the x coordinate of N and x coordinate of P are same, and this is a point on a straight line, therefore on the x-axis, therefore we can say that that the coordinate of N should be 80 square comma 0. That should be the coordinate of the point N, because this point N lies on x-axis, that is actually the axis of the parabola. And P has this kind of coordinates 80 square comma twice 80. So we got the coordinate of the point N. Alright, and we know the equation of tangent. This should be y is equal to tx plus y plus tx is equal to 80 square plus twice 80, although the printing is not very good. Y plus tx is equal to twice 80 plus 80 cube. This would be the equation of tangent. So if we put the what is the equation of x-axis? X-axis equation of x-axis is y is equal to 0. So if we put y is equal to in this equation, we will get x is equal to twice a plus 80 square. The printing is not good at all. Twice a plus 80 square. Okay, so in this fashion, this is the equation of normal. Sorry, so this is the equation of normal. So this normal will intersect the x-axis at the point G. Therefore, the coordinate of the point G would be like this: a twice a plus 80 square comma 0. What we are doing, we are just considering the equation of normal, and then in this equation of normal, we are putting y is equal to 0. Why y is equal to 0? Because y is equal to 0 is the x-axis. Just we are considering the intersection of x-axis and the normal. So in this fashion, we can find the coordinate of the point G, the intersection of x-axis and the normal, and this would be the coordinate of the point G. In the same fashion, we can again find the coordinate of the point capital T. Got it? So, so over here, you see the result that generally comes in exam is that the subnormal is of constant length. Subnormal of a parabola is of constant length. What is subnormal? Subnormal is this much distance ng. This much distance ng is the subnormal. You see, we got the coordinate of the point G and the coordinate of the point N. Then what would be ng? Ng is equal to ng is equal to ag minus an. Okay, ng, this ng, this much length ng is equal to the total length ag minus this much length an. Okay, and what is ng? Ng is equal to sorry, what is ag? Ag is equal to it twice a plus at square, because ag is the this x coefficient, x coordinate of g, and an is equal to the x coordinate of n. So you just subtract these two coordinates, x coordinates of g minus x coordinates of n, then you will get is equal to twice a. So twice a is a constant quantity. Therefore, length of subtangent is always equal to the constant value twice a. Sorry, not subtangent, subnormal. The length of subnormal is equal to the constant value twice a. So this much is the first part of the question. Subnormal of a parabola is always constant. Okay, and the remaining portion is that it says that this subtangent, this Tn, this much length, this much subtangent is bisected at this point capital A. That means the distance TA, this distance TA and the distance AN, this much distance AN, these two distances must be same. The distance TA, this much distance TA and the distance AN, this much distance must be is equal to same quantity. Okay, so how to prove this result? If we already got the coordinate of n, what is the coordinate of n? Coordinate of n is equal to 80 square comma 0. This is the coordinate of n. Now if we find the coordinate of t, you will find the coordinate of t becomes is equal to minus 80 square. I am not showing this result. You will have to show this result in your exam. The coordinate of t is equal to minus 80 square comma 0. Got it? The coordinate of t would be is equal to minus 80 square comma 0, and therefore this expression, the coordinate of the point capital A, what is this? Capital A is actually the origin. If you look at this picture, and then this y-axis would ultimately cross through this point, the vertex capital A. So capital A would be the origin. So you see the distance from A to N, that is actually 80 square, and distance from A to T, that is again 80 square. Just this negative sign comes because of the fact that T lies on the left of the point capital A, and this positive sign means N lies to the right of the point capital A. So plus or minus sign, it represents just the direction, but the distance from A to N is equal to this 80 square, and distance from T to A is equal to again 80 square. Therefore, these two distances are same, or in other words, we can say that capital A actually bisects the length Tn. Now, is it clear to you? That's why it says that the subtangent is bisected at the vertex. This subtangent is bisected at the vertex of the parabola. Is it clear to you?
Clear, sir.
So, to finish this class, I would like to introduce the definition of pole and polar. This is the polar, And related to this point, related to this definition of polar, there is one more definition that is called the pole. I am not going to discuss this equation of pole and polar. I shall discuss all these results in the next class. Hmm. Just I am trying to introduce the definition. Okay. Let me show you a picture for you. Suppose we have a curve like this. Say we are considering an ellipse. Hmm. And there is one point P. Let me magnify this one a bit. Hmm. This is the point P. Okay, this is the this curve, suppose this curve is the ellipse, and we have a point P situated over here. This is the point P. Hmm. And through this point P we draw any arbitrary straight line passing through the point P. We draw any arbitrary straight line like this kind of point. Hmm. Let me change the color. Suppose this is the straight line. Hmm. We are drawing any arbitrary straight line through this point P. Okay. Now we know that any such straight line can intersect the any second degree curve. Okay, any straight line can intersect this kind of second degree curve at most at 2 points. This is one point. Let us I am calling it capital A. This is the point capital A, and this is the point capital B, suppose. Hmm. And now we draw two tangent two tangents at the point capital A, tangent to this ellipse, to this curve. It may be an ellipse, it may be parabola, it may be hyperbola, it doesn't matter. Any second degree equation, any second degree curve. Hmm. So we are drawing two tangent lines. This is one line. Let us denote it by blue color, and this is suppose another line. Let us denote it by say this kind of orange color. Hmm. Now what I am doing, we are keeping this P fixed. Be very careful. Try to observe over here. We are keeping this point fixed. We are not changing the coordinate of the point P. We are keeping this point P fixed, and then we are changing this straight line AB. The straight line always passes through the point P, but just we are moving this kind of straight line. You see, we can change the position of this straight line. The straight line always passes through the point P. Okay, and you observe that these two tangents have a point of intersection like Q. This is the point, suppose Q. The point of intersection is taken as the point Q. And as we change the position of AB straight line, this is the AB straight line passing through the point P. P is fixed. But as we change the position of this straight line, you see the position of Q is also changing. Okay. Now I am saying that the locus of the point Q, we are we are defining the fact that locus of the point Q is called the polar. Locus of the point Q is called the polar, and we are going to show after in the next class, of course, we shall show that this polar is nothing but a straight line. You will get this kind of equation, this kind of equation of the polar, that would be the equation of a straight line. Got it? And over here I am not going to show that this is a straight line, just I am pictorially showing this. So I am just showing this graph. Suppose let me show you the locus of this point Q. I am just changing the point B. Just see, try to observe over here the locus of the point Q over here. Slowly I am just changing it with very slowly. So ultimately you will get this kind of straight line. And suppose I am moving this point B over here. Over here you see this would be the position over here. It is this line. Hmm. This line. If I change the position of B, you will find that the position of Q, this point Q, actually describes a straight line, and this straight line is called the polar line. This line, this kind of bold line, this line is called the polar line, or simply the polar. This line is called simply the polar line, or polar, simply the polar. Hmm. This locus of the point Q is called the polar line, or simply the polar, and this point P, okay, this fixed point P is called the pole of this polar line. Okay, again I am saying that this fixed point P is called the polar, this fixed point P is called the pole of this polar line. Polar line is actually the locus of this point Q, and this point P is called the pole of that polar line. Now, how to obtain the equation of polar line, or simply the polar, if the point P is given, or conversely, if suppose this polar line is given, and then how to compute the pole of that point P, that I shall discuss in the next class. Thank you for being with me in this class.